In this video, we want to solve problems number 1 and 2 from British Mathematical Olympiad BMO round 2 2023. Let me show you the problems or what problems are 1, 2. Let me show again 1, 2, 3, and 4. And we will solve 1 and 2 and we will analyze. In other videos, I will release 3 and 4. And let me tell you something. For 1 and 2, we won't only solve these two problems. We want to analyze important ideas. And before BMO round 1 2022, 2023, I released a video preparation. In that video, I told you a lot of important things, and I use many of them in BMO round 1 of this year. Also, I will use again same ideas for solving 1 and 2. And you should learn general ideas that are useful for BMO round 2, BMO round 1, AMC, AME, CSAT, SAT, the exams for applying top universities. So let's see how we can solve this problem. Let's start with problem number 1. It says let ABC be a triangle with an obtuse angle A and in center I. So let me draw the figure. Okay, it is a figure. A obtuse angle A, in center I. In center means intersections of angle, internal angle bisector, and it is also center of in circle, the circle that is tangent to all three sides. Circle ABI and ACI, ABI, ACI intersect BC at again an X and Y. And let me tell you something, BMO and BMO is for UK, AMC, USA, AMO, all these things are for USA. These two exams are most prestigious exams in Olympiad in the world, in national level. Okay, so it says circles ABI and ACI intersect BC again at X and Y. Okay, look, this circle, X and Y. The lines AX and BI, AX, BI meet at P, this point. And the lines AY and CI, AY, CI meet at Q. Prove that BCQP is cyclic. BCQP. Okay. When we want to prove that a circle is quadrilateral is cyclic, there are 4 rules. 2 of them related to angles, 2 of them related to lengths. For example, if ABCD is cyclic, the first rule is that you say, okay, ABCD is cyclic if and only if ABCD is cyclic if and only if A plus C is 180. One rule is this. The other rule, you can say 2. Let me copy this one. If the first 2 rules related to angles, this one says that if we connect this, A1 equal to B1 if and only if ABCD is cyclic. Means the angles that see the same side are equal. It was second rule. Third rule, ABCD is cyclic if we draw the diagonals. It is related to lengths. If we consider intersection P, then we can say ABCD is cyclic if and only if AP times PC equal to BP times PD. And the last one, fourth rule. Let's draw. You should extend the 2 sides here. And look, each of them has proof, and the proofs are basic. You can use without proof because they are so much famous in exams that needs full solution. So here again, ABCD is cyclic if and only if PA times PD equal to PB times PC. So we should select from these 4 things which of them useful here. If we want to work with angles, PQ, look, we should prove BCQP cyclic. So if you, for example, draw this angle is good. It's B half because BI is internal angle bisector. But here it's a little hard to work with. And also we will see angles are not so much good. And if you want to use third rule about lengths, we should consider the diagonal. Again, we will say, okay, we should draw two new lines. So let's see what about fourth condition. We should extend. And here you will see that I is the intersection of extensions of CQ and BP. So because we don't need to draw any new line, let's check this one first. Okay, so we prefer not to draw too many lines and consider angles that we should draw new lines. So here I say PQCB is cyclic by fourth rule that I told you now, if and only if IP times IQ equal to IP times IB, equal to IQ times IC. IB and IC are better than IP IQ because IB, look, it is B, we know it is vertex of the triangle ABC and I is in center. So we should focus on IP IQ. Let's consider something. We know these two angles are equal. Both of them are B half. So, and it is a cyclic quadrilateral. So these two arcs also are equal because they are opposite to these two angles. Now let's draw lines. This line, this line, this line. Then we can say, okay, this is for some 1.1 point angle. It is equal to this. Why? Because it sees this one. See the same arc. And they are inscribed angle, half of the arc they see. Also, these two angles are equal. So we can say these two angles also are equal like this. Okay. So because these two angles are equal, IAP, let me call this one, for example, I want to say IA equal to IX. Look, angle IAX equal to angle IXA. So we can say the IAX is isosceles triangle, IA equal to IX. These two lengths. Also, we can say, because it is C, these two angles are equal to points, because CI is internal angle bisector, this is equal to this one equal to this one, so we conclude that these two angles also are equal, and we can say because angle IAY equal to angle IYA, so we can conclude IA equal to IY. Now, because IA is same, we conclude that IA equal IX equal IY. Okay? Now we want to see how we can relate it to IP. Now I want to, for finding IP, I want to use a sine rule in this triangle. Okay? A sine rule for preparation of BMO 1 and also AMC. I released video before that. I told you sine rule, cosine law, all these things, and I explained are important in many math exams like here. So we should focus, we should use a little angle chasing. We know one point is B half. So this angle is also B half. And we know this angle is A half because AI is internal angle bisector. This angle is B half because it is one point, it is this. So we can say this angle is A half minus B half. Okay, if you have any question, feel free to send message to my WhatsApp number in the description and comments. So look here, A half, B half. Why it is B half? Because it is equal to this. They see the same arc. One point is B half. The whole part, because AI is internal angle bisector, is A half, so it is A half minus B half. And we know this one is also B half. And now we can say this angle is what? This angle is exterior angle of this triangle. Okay, so it is sum of non-adjacent angles. A half minus B half plus B half. So it will be A half. Okay. Now let's use sine law in triangle PXI. Sine law in triangle PXI. So we can say IX over sine. Look, we should consider sine this angle. It is what sine 180 minus a over 2 equal to pi. Pi over sine b over 2. Pi over sine b over 2. And let me tell you, here we should prove this because we want to prove PQCB cyclic. The other things are assumptions and the conclusions we've reached. Now, let's focus on this. We know that sine 180 minus some alpha, for example, equal to sine alpha. So we can say Ix over sine A over 2 equal to Pi over sine B over 2. So we can say Pi equal to sine B over 2 over sine A over 2 times Ix. Now, Pi is for what? For part B from vertex BBC. IQ is what you see from vertex C. So all things are same, only here you should see from C. And similarly, we can say that IQ equal to sine C over 2, because B changes to C, A same, A over 2, times, instead of IX, because IX was related, you should say IY. And we know all of them are equal, IY. Now, we want to find, for example, IP over IQ. Let's divide, okay? Divide these two terms. So PI over IQ, let's see, it is equal to what? Sine B over 2 over sine C over 2. Sine A over 2 will be cancelled times IX over IY. And we've proved IX equal to IY. We can call it a star. I star, you can cancel that. And you can say it is equal to sine B over 2 over sine C over 2. Now, if you consider triangle BIC, okay, triangle BIC, we can say IB over sine C over 2 equal to IC over sine B over 2. Okay, so we can conclude, let me write it here, IB in triangle BIC sine law. Sine law IB over sine C over 2 equal to IC over sine B over 2. And because here we want what? We want sine B over 2 over sine C over 2. So we conclude sine B over 2 over sine C over 2 equal to IC over IB. So we can write here it is equal to IC over IB. Now, if we cross multiply, we consider this term, we conclude Pi or IP times IB equal to IQ times IC. It was exactly the thing that we wanted. IP, IB, IQ, IC. IP, IB, IQ, IC. We proved this. So by fourth rule, we proved PQCB is cyclic. Okay. So here, look, we only needed fourth rule, but I told you all four rules that are useful in some problems. Only first one useful, sometimes some of them useful. You need to apply more than one of them. It was related, and it is also useful in AMC, AME, USAMO, IMO, cyclic quadrilaterals are so much important on how to apply. Also in BMO 1, in many years, it's useful. So if you want to learn other important formulas, and as I said before, there are around 40-50 formulas in geometry, also in other topics, combinatorics, number theory, algebra, you should memorize them. If you want to learn them, feel free to send message to my WhatsApp number in the description and comments. Now we can solve, we can jump into problem number 2. Problem number 2, it says for an integer n greater than 1. Before solving this, before BMO preparation, I told you, and also before AMC, before BMO 1, I released the video. Exactly, I told you the idea here. For these types of problem, you should consider small examples and find the idea and generalize that idea. In many cases, you should use also induction. So let's read. It says, and again, we solved this problem with the same idea also previous year. We had problem that was in all years. We have problems that we can use this idea. So if you want to learn how to apply this important idea, considering a small example, how to find not only pattern, you should find idea behind the problem and then generalize that. How you find the idea behind the problem? By considering a small example. So it's an important technique. So, and strategy. So let's read. For an integer n greater than 1, the numbers 1, 2, 3 to n are written in order on a blackboard. The following moves are possible. Take three adjacent numbers x, y, and z, whose sum is a multiple of 3, and replace them with y, z, x. The next rule. Take two adjacent numbers x, y, whose difference is a multiple of 3, and replace them with y and x. For example, we could take, so let's see, it says 1, 2, 3 to this one, but first rule. Let's see, 2, 3, 4. The sum of 2, 3, 4, because it says the sum should be multiple of 3. For example, look, 1, 2, 3 also, the sum is 6, 2, 3, 4 is 5 plus 4, 9. So you can apply first rule, then 4 will, let's see, sorry, for 1, 2, 3 it applies. So, for this one, 3, I like this one, x, y, z, x goes to the last one. First one goes to the last one, 2, 3, 1. And then second rule, it says we apply for 1, 4, because their difference is multiple of 3, 4 minus 1, 3. You switch 4 and 1. And then it says find all n such that the initial list, which is 1, 2 to n, can be transformed into n, 1, 2 to n minus 1 after finite number of moves. Okay, because it says n greater than 1, let's check n2. 1, 2, you should change it to 2, 1. Is it possible? No, because we have only two elements. So n2 is not possible, and their difference is not multiple of 3. Let's check n3. We want to see, is it possible to move 1, 2, 3 to this one? 3, 2, 1. So 1, 2, 3, if we apply first rule, then you can say what? Let me tell you something. It says you can reach from x, y, z to x, y, z. If you apply this again, look, first one goes to last part. It goes to last part, it will be z, x, y. If you apply this again, you will reach again x, y, z. So as you can see, it seems that, for example, x, y, z lie on a circle. Okay, so as you can see, let me correct this one because it is 3, 1, 2. So for better simplification, that is useful in, also in SUMAC, this idea was useful, Stanford summer camp. You can say, for example, you can rotate x, y, z clockwise in each step 1 unit. And let me tell you, if you rotate it twice clockwise, it is equivalent to once counterclockwise. Okay, because when you rotate it 3 times, it will be same. So 2 clockwise is equivalent to 1 counterclockwise. So it means that for working with second rule, you can consider any 3 terms. You can rotate it circular, clockwise or counterclockwise. Now, for example, here you say, okay, we will rotate 3 here, 1, 2. So with one action, you can reach this. Now, so n3 was okay. Let's check another numbers. For example, n4. 1, 2, 3, 4. We want to reach 4, 1, 2, 3. So, because we want to move 4 from last one to first one, we consider this part first. 4 plus 3, 7 plus 2, 9. So you can rotate and we can reach. So here we want to reach how? We want to see how we can reach. So you can say 1, 4. After 4 is 2, then 3. We rotate. Now 4, 1. The difference of, so it was second rule. From first rule, you can use this, you can switch 1 and 4 because their difference is multiple of 3 is 3. So it will be 4, 1, 2, 3. So with first rule, we can reach this. So N4 was also okay. Now, let's check next one. N5. So we have 1, 2, 3, 4, 5. We want to see, can we reach to 5, 1, 2, 3, 4. Okay. By first rule, if I want to 5 plus 4, 9 plus 3, 12, for example, if we use this, we can say, okay, I move it 5 here, then 3, then 4. Then 5, 2, their difference, 5 plus 2 plus 1 is not multiple 3 if we apply it, so second rule. If we apply first rule again, you can switch 5 and 2, it will be 1, 5, 2, 3, 4. So now we can't do this, but here you can't say 5 is not possible because maybe we couldn't, for example, do this. Someone can do something better and reach. So we don't know. And 5, we couldn't find a way. So let's, and we guess. Look, I draw with dotted line because we guess that N5 is not possible. Because if you check many cases, you will see it's not possible, but we've not proved yet. Okay, we are just working on the solution and we don't write these things on an answer sheet. All things are for ourselves. Then we guess which numbers are okay, then we try to prove. After that, we write the solution on answer sheet. So let's check N6. If we work on N6, we want to reach from 1, 2, 3, 4, 5, 6 to 6, 1, 2, 3, 4, 5. Okay, so for 6, sum of 6 plus 5, 11 plus 4, 15. We apply second rule. It will be 1, 2, 3, and 6, 4, 5. Now, if we use first rule, let me see second rule, third rule was what? Second rule? Second rule, only 2 elements, so I think I should correct. Second rule, 1, 4, 3. Okay, so this was first rule, this was second rule. Okay. And this one, 1, 2, 3, second rule, no. First rule, second rule, and here. By first rule, we can reach this. Now, by second rule, we switch 3 and 6 because their difference is 3 and multiple of 3. 1, 2, 6, 3, 4, 5. Then here, 1, 2 plus 2 plus 6 multiple of 3. If we apply first rule, we can rotate. Look, we see how many times we need. We rotate such that 6 comes here, 1 comes here, 2 comes here, 3, 4, 5. So we could, for N6, it was possible also. Let's check N7. Here, look, we guess all things are related to 3. 3k, 3k plus 1 possible, 3k plus 2 is not possible. So, for 5, let's see 7 is possible or not. So, we want to reach from 1, 2, 3, 4, 5, 6, 7, 2, 7, 1. Okay, so 7, 1, we want to see is it possible to reach 7, 1, 2, 3, 4, 5, 6. Again, we focus on 7 to take it to first place. So if we consider this one, sum of them multiple of 3, and we apply first rule, it will be 1, 2, 3, 4, 7, 5, 6. Now we apply second rule for this part. It will be 1, 2, 3, 7, 4, 5, 6. Then 7, 3, 10, 12. We apply first rule here. It will be 1, 7, 2, 3, 4, 5, 6, and then we apply second rule for this part, and we will reach the arrangement we wanted. Okay, so it was possible. Now we guess. We guess that n equal to 3k. Okay, 3k plus 1. Okay, 3k plus 2 is not okay. Now, for 3k plus 1, it is our claim. We want to prove this. So we should consider three cases. For 3k, y we can, for 3k plus 1 again, y we can, and y for 3k plus 2, no one can reach the destination, the last permutation the problem wants. So we have three cases. In first case, let's consider n equal to 3k and let's solve. We want to reach from 1 to 3 to, for example, 3k minus 4, 3k minus 3, 3k minus 2, 3k minus 1, 3k. How we can reach from this to this one, that 3k, 1, 2, 3. We want to take 3k to last part. 3k, for example, minus 2, 3k minus 1. Okay. So let's start. We can say we have 1, 2, 3. Let's consider 4, for example. 3k minus 4, 3k minus 3, 3k minus 2, 3k minus 1, 3k. In first level, you see their sum is multiple of 3 because it's 9k minus 3. So we can move 3k here, 3k minus 2 here, 3k minus 1 here, and then 3. So by which rule? By first rule. And 3k minus 3, 3k minus 4, and 1, 2, 3, 4. Okay. Now from this part, we can use second rule to apply this one. So it will be 1, 2, 3, 4, 2, 3k minus 4, 3k, 3k minus 3, 3k minus 2, 3k minus 1. Now let me tell you something. Here you can do again this thing 3k, 3 ones and 1 1 like this, or we can use induction. You can say here we have 1, 2, 3k minus 4, for example, like this one is similar to 3k minus 3 because both of them are multiple of 3. So we can reach this by induction to 3k, 1, 2, 3, 4, 3k minus 4, and rest. So we've used what here? We've used 3k minus 3 and reached 3k. Okay, and so in base case, for example, you can say, okay, you checked 2, it was not possible, 3, and because we want to only prove the things we want for this case, for case 1, you need base case 3. Okay, and so 3k minus 4 and the rest, or 3k minus 3, 3k minus 2, 3k minus 1. So we prove first case by induction. Now let's consider second case, which n equal to 3k plus 1. Again, we write all things we have. 1, 2, 3, 4, 3k minus, for example, 5, 3k minus 5, 3k minus 4, 3k minus 3, 3k minus 2, 3k minus 1, 3k, 3k plus. And then, if we use first rule here, their sum is multiple of 3. It will be 1, 2, 3, 4, 3k minus 5, 3k minus 4, 3k minus 3, 3k minus 2, and here 3k plus 1, 3k minus 1, 3k. It was now we use second rule to switch these two things. It will be 1, 2, 3, 4 to 3k minus 1, 3k minus 4, 3k minus 3, 3k plus 1, 3k minus 2, 3k minus 1, 3k. And look here, if we consider this one, you can use induction. And we can say again 3k minus 1, the next one is 3k minus 2. And both of them, 3k minus 2 and 3k plus 1, both of them, the remainder when divided by 3 is 1. So they will be same. Because the two rules, mod 3 is important, divisibility by 3. So because these two numbers are same, we can use the same thing. We can use induction. And this case 1 and 2 were same. We could also say 1 to n and use the same thing from n minus 3 to n. So then we can prove part 1 and 2 with one step. So we can do 3k plus 1, 1, 2, 3, 4, 3k minus 5, 3k minus 4, 3k minus 3, and then also we have these things, 3k minus 2, 3k minus 1, and 3k. Okay, we could reach this one, and we proved that if n 3k or 3k plus 1 is okay. Now we should prove that 3k plus 2 is not possible. For 3k plus 2 that is not possible, we should use invariant. We should define a function. And look, the most important thing is how to find a good function. So n equal to 3k plus 2, because look, when we want to change, for example, two numbers, let me tell you, for example, 5. We want to reach from 1, 2, 3, 4, 5 to what number? To 5, 1, 2, 3, 4. If we consider mod 3, the first arrangement is 1, 2, 0, 1, 2, and we want to reach 2, 1, 2, 0, 1. Okay? We want to say it is possible. It is impossible. So the first rule was what you consider, for example, 3 elements. We want to say also it is not possible to reach from this arrangement to this arrangement. Also for mod 3, if you consider it is not possible, so we can say the main part also is not possible. So in first rule we said if x, y, z, the sum of them multiple of 3. Sum of them, x plus y plus z, is multiple of 3. So what are the cases? One case 0, 0, 0, 1, 1, 1, 2, 2, 2, 0, 1, 2. Now we will see that 0, 0, 0, if you change them again, it will be 0, 0, 0. So it has no effect, only we should consider 0, 1, 2. Okay? So for example, if you have 0, 1, 2, you can rotate it. You can go to 2, 1, 0, or you can go to, you can rotate it again, 0. Sorry. Let me correct this. After 2 is 0. 2, 0, 1. And if we switch again, it will be 1, 2, 0. And if we start with 0, it will be this. So we can change it to these two things. And for second rule, it says if two things are same when divided by 3, their difference multiple of 3. So we can say x, it is x, because we only consider mod 3. You change it to x, x. So it has no effect on our arrangement when we consider mod 3. So our only movements are this. We can move, for example, 0, 1, 2 to 1, 2, 0 or 2, 0, 1. Now, the most important thing, what is our function? I want to define a function that, for example, f here is something, f here is something, but under this condition, this movement, this action, f won't change. F is stable. It is invariant. This is so much important lesson. Many problems of SUMAC, Stanford Mathematics Camp, Stanford University Mathematics Camp, could be solved 2023, 2022, could be solved by invariant, but you should define function. It's not so much easy, but if you solve some problems, you will get what functions are good. So here I define, let me explain for you. I define one function. For example, suppose the first element is 1, it is a1, it is 2, it is a2, it is 3, it is a3, and so on. For example, it is n, it is an. We define f as 1 times a1, the position times the number inside, 2a2, 3a3, up to nan. Okay, we define f as this. Now, let's see for this example, then we generalize for general n3k plus 2. Here, and we consider f mod 3. This is the first place, the second place, third place you can say it is 0. Fourth place, again you can say it is 1. Fifth place, it is 2. So f here, let's calculate. is 1 times 1. We consider mod 3 all things. 1 times 1, 2 times 2, 4. It is 1. So it will be 1 plus 1 plus 1 plus 1, which is 4 here, which is 1. Okay, we consider mod 3 all things. Here, you say here, it is 1, first place, second place, third place, again, fourth place, second place. It will be 2, 2, 2. So it will be 2 plus 2 plus 2 again, which is 6, which is 0. So f1, 0. Now, I want to prove that f won't change under these actions. So let's see. For example, suppose that it is, for example, it is I plus 1, it is I plus 2. And we have x, y, z, and we know x plus y plus z is multiple of 3. Okay? So let's see if f won't change mod 3, it will be good. So suppose, for example, you rotate. You say, okay, z comes here. If we consider the first action of 2, y, z, x. Okay. So x goes to the end. So we can say x, and then we consider y, z. But the previous part was also okay. Rotation it is. I explained the beginning of the video. So let's see under this action what's the effect on f. So the first part is xi plus I plus 1y plus I plus 2z. Now let me tell you something. Because x plus y equal plus z is 0, so we can say z equal to negative x minus y mod 3. So you can replace by that. So if you replace with that, it will be mod 3 xi plus I plus 1y plus I plus 2. Instead of z, we replace it with negative x negative y. Okay? So it will be ix plus iy plus y minus ix minus iy minus 2x minus 2y. Ix, iy, iy. So it is congruent to plus y minus 2x. It is the first part. Now let's apply second part. This iy plus I plus 1z plus I plus 2 times x. And it is congruent to iy plus I plus 1 z, which is negative x minus y, plus I plus 2x. It will be iy minus ix minus iy minus x minus y plus ix plus 2x. Ix negative ix will be cancelled, negative iy will be cancelled. 2x minus x is x, and it is x minus y. Okay, now I want to prove that these two things are congruent mod 0, mod 3. So this part and this part. So if I want to check this, I can say, okay, minus y minus 2x is congruent to x minus y is equivalent that you add 2x plus y to both sides. So left side will be 0, right side will be 3x plus y will be cancelled. So 3x is congruent to 0, mod 3, it's okay. So we will see under this action when we do this, it has no effect on f. So here f was 1, f here is 0, so it is impossible to reach this. Now we want to do this for other 3k plus 2. So let's prove in general. Suppose n is 3k plus 2. The first configuration is, you say, in first place, you have 1. In second place, you have 2. In third place, like this. Let me show you. In third place, you have 0. Third place, you can say 0, 0. In fourth place, which is 1, you have 1. In fifth place, you have 2. It's 2. In sixth place, it's 0, 0. So for 3k plus 2, it is 0, 0, 1, 1, and 2, 2. Okay. Now it wants to reach 3k plus 2 here. So 3k plus 2 will be here, and then 1 here, then 2 here, then 3 here, 0, then 1, 2, 0, And 3k plus 2. 3k plus 1. The last one will be 1, 0, 2, 1, 0. And here it will be 1, 2, 0, 1, 2, 0, 1. And the last one, if we want to consider the cases, it's 3k plus 2 is 2, 1, 0, 2, 1. Okay. Now f here is what? 1 times 1, 2 times 2, all of them. 1 squared plus 2 squared plus 1 squared again plus 2 squared up to last one. So if you consider mod 3, all of them will be 1. And we have how many 3k plus 2 terms? How many 0 are there? Minus k. It will be 2k plus 2. Mod 3, it will be, yes, 2k plus. Let's consider something. Now, look at small example. Here you write this in your answer sheet, but you have these things you can check. For example, for this part, it says f equal to 1. Here it was 5, and 3k plus 2 is 3, 1 plus 2. So 2k plus 2 to 1 plus 2 will be 2 plus 2, 4 is 1. So here we've reached 2k plus 2. Now we want to consider f for this part. It is 2, again plus 2, then you have 2 zeros, okay? Then you reach 2, then you reach 0, then you reach 0, okay? And so we will see here, we have 2, 0, 0. Again, we have 2, 0, 0. So from here, we have something like this. Again, 2, 0, 0. Plus the last part, 2. So how many 2's are there? 3k. We have 3k plus 2 numbers. You subtract by 2, 3k over 3 plus 2 other 2's here. So it will be 2 times k plus 2, which is 2k plus 4. Okay. So if you consider mod f won't change mod 3 under the actions the problem wants. So if we can reach by contradiction 2k plus 2 should be congruent to 2k plus 4. Then we conclude 2 is congruent to 4. If we subtract by 2, 0 is congruent to 2 mod 3, but it's not correct. So we consider that if we reach, then we've reached contradiction. The most important part of this problem was defining this function. Maybe you say, okay, from what place I understood this function is good? Like there are some, for example, sum of production, sum of squares, sum of variables, product of variables. There are some general things like these. In many problems, they are useful. And look, it was not the first function I've checked and was correct. I checked different functions. Many of them were wrong. And then I reached this function that works. Okay, so if you want to learn these things and the ideas, as I told you, important ideas in combinatorics, 40, 50 important formulas and ideas you should learn in geometry, combinatorics, number theory, and algebra, useful in BMO, IMO, AMC, AME, USAMO, and other national Olympiads, and also International Olympiads, IMO. If you want to learn them, feel free to send message to my WhatsApp number in the description and comments.